Lesson 6.6, De Moivre's theorem. In this lesson, we're going to be working with complex numbers. First, how to plot complex numbers, then how to find the modulus or absolute value of a complex number. We're also going to be multiplying, dividing complex numbers. Then at the end, we're going to talk about how De Moivre's theorem can help us quickly find values of complex numbers raised to some power. First, we need to talk about the complex plane, which is going to be very similar in how it looks compared to the xy axis that we've talked about in the past, the regular coordinate plane. So instead of having an x and y axis, we have the real axis and the imaginary axis. So if we have a real number in the form a plus bi, a represents the real portion, the expression bi represents the imaginary portion of the complex number. First, we're going to use what we're used to as the x-axis as a real axis, go over that distance, and then we're going to go up the imaginary portion. So that's how we plot the complex number a plus bi. We have the real axis and then the imaginary axis. So to the right, we have the example. We have the complex number 2 plus 3i. First, we're going to use the real portion. So we go over 2 units on the real axis, and then we go up 3 units on the imaginary axis. So another example, suppose I wanted to plot the number 3 plus I. So my real portion is 3, the imaginary portion is 1, understood to be a 1 in front of there. So I would go 3 units in the real direction and then 1 unit in the imaginary direction. So that would be the complex number 3 plus I. Next, we're going to talk about the modulus, which is simply the absolute value of a complex number. It's common to use the letter z to represent the complex number, so z is equal to a plus bi. If we want to find the modulus, or the absolute value, all we're going to do is take the square root of our real value squared plus the imaginary value squared. So if we look at that in the complex plane, the modulus is referring to the distance from the origin to our complex number. Now we're going to look a little further at the values of our complex number. So we have our complex number a plus bi plotted in the complex plane. We have our distance along the real axis, which represents our value a, and the distance along our imaginary axis represented by the value b. We can see that a is equal to r times the cosine of theta, and b is equal to r times the sine of theta. So where the heck do these expressions come from? Why is b equal to r times the sine of theta? Well, since we have a right triangle, we can use SOHCAHTOA. So if I have my angle theta, I know it's the opposite over the hypotenuse. So the sine of theta is going to be equal to the opposite, which was length b, the imaginary portion, over r, representing the radius of this right triangle. Now, if I wanted to get b isolated by itself, I would multiply r to both sides of the equation. So we get r times the sine of theta is equal to b. We could use a similar process to determine see why a is equal to r times the cosine of theta, because if this is our angle theta, the cosine of theta is equal to adjacent over hypotenuse. Go through the same process. The reason we need to know that b is equal to r times the sine of theta is going to be in the next example when we talk about complex numbers written in polar form or trig form. Now we're going to discuss another way to express a complex number. This is going to be the trig form of the complex number, also referred to as the polar form. So if z equals a plus bi, then we can rewrite that as z equals r times the quantity cosine of theta plus I times the sine of theta. So we have our real portion and the imaginary portion. A is represented by r times the cosine of theta. B is represented by r times the sine of theta, which we just talked about in the previous slide. R is equal to the square root of a squared plus b squared, and tangent of theta is equal to b over a. So the value r, that is just going to be the modulus or absolute value of our complex number, and the angle theta is referred to as the argument of our complex number. Now to an example down below, find the trig form with theta between 0 and 2 pi for the complex number 1 plus radical 3i. So we can have z equals 1 plus radical 3I. We know we're going to be in radian form when we go through this process because of our angle theta is between 0 and 2 pi. Those are radian measures. So if we want to write this in trig form, two things we're going to have to find. First, we have to find the absolute value or the modulus, the value of r. And then we also have to find angle theta, which is referred to as the argument. First, to find the modulus, the value of r, we know r is equal to the square root of a squared plus b squared. My value of a in my complex number is 1, so I'm taking 1 squared plus the value of b is radical 3. So I have 1 squared plus radical 3 squared, taking the square root of that result. 1 squared is 1, radical 3 squared, the square root and the squared cancel each other out. So 1 plus 3 is 4, the square root of 4 is 2. So the absolute value or modulus of this complex number is 2. Now I need to find the value of theta. And we have this expression. We're told the tangent of theta is equal to b over a. So the tangent of my angle theta is going to be equal to my b value, which is radical 3, divided by my a value, which is 1, which just simplifies down to radical 3. Now to get theta by itself, we would have to take the inverse tangent to each side of the equation. So theta is equal to, good equal sign, theta is equal to the inverse tangent of radical 3. And you should use your unit circle to find this value. So tangent is equal to sine over cosine. So you're looking for the ordered pair where the sine value divided by the cosine value would simplify down to radical 3. And that occurs at pi over 3. So now we found our modulus to be 2. We know our argument, the value of theta, is pi over 3. Now we can plug that into our form for the trig form or polar form to find the way to rewrite this complex number. Thus we get z equals 2 times the quantity of cosine of pi over 3 plus I times the sine of pi over 3, which we could also rewrite as 2 times the cosine of pi over 3 plus 2I times the sine of pi over 3. So to rewrite a complex number into trig or polar form, you have to find the modulus r, and you have to find the argument, which is the angle theta. Next, we're going to talk about how to multiply and divide complex numbers. So let z sub 1 be equal to r sub 1 times quantity cosine of theta sub 1 plus I times the sine of theta sub 1. And z sub 2 is equal to r sub 2 times the quantity cosine of theta sub 2 plus I times the sine of theta sub 2. The first equation tells us how to multiply two complex numbers. So we are multiplying the modulus of each of those complex numbers, and then we're going to add the arguments for each of the complex numbers. So we're multiplying the r values, the modulus, and then we're going to add the arguments, the theta values. If we're dividing two complex numbers, then we're going to divide the modulus for each of our complex numbers, and then we're going to subtract our arguments for each of the complex numbers. Just making sure if we're dividing that the modulus of r sub 2 cannot be equal to 0. Now an example down below, we want to express the product of z sub 1 and z sub 2 in standard form. Z sub 1 equals 4 times the cosine of pi over 4 plus I times the sine of pi over 4. Z sub 2 is equal to radical 2 times the quantity cosine of pi over 6 plus I times the sine of pi over 6. So if we want to find the product, we're going to use the first equation. So the product of z sub 1 times z sub 2 is going to be equal to, we have to multiply our modulus together for each of those complex numbers, and then we have to add the arguments together for each of those complex numbers. So first we get 4 times radical 2 times the quantity, the cosine of pi over 4 plus pi over 6 plus I times the sine of pi over 4 plus pi over 6. Next we need to simplify these arguments. So get a common denominator and add pi over 4 and pi over 6. Now we get 4 times radical 2 times the quantity of cosine of 5 pi over 12 plus I times the sine of 5 pi over 12. So here is our polar form. We want to find it, the complex number in standard form. So we're simply going to calculate the value of the cosine of 5 pi over 12 and multiply that result by 4 radical 2. Then we're going to calculate the value of the sine of 5 pi over 12 and multiply that by 4 radical 2. Thus, for the standard form of this complex number, we get 1.464 plus 4.464i. We have our a value, the real portion, and our b value, the imaginary portion. The last thing to talk about in this lesson is de Moivre's theorem, which allows us to find the value of some complex number raised to a positive integer. So if z is equal to r times the cosine of theta plus I times the sine of theta, as long as we're in trig or polar form, and n is a positive integer, then z to the n, that complex number raised to some positive integer, all we're going to do is take our modulus, the value of r, raise it to that n power, and then we're going to multiply our arguments by the value of n. So raising the modulus to that power of n, multiplying each of the arguments by that value of n. Now a quick example using de Moivre's theorem. Suppose we have our complex number z equal to 2 times the cosine of pi over 3 plus I times the sine of pi over 3. Our complex number has to be in polar form. If it's in standard form, we have to go through the process of rewriting it in polar form like we did previously. We want to use de Moivre's theorem to find the value of z cubed. So applying de Moivre's theorem, we're going to take our modulus, which was 2, and raise it to the power of 3. And then we're going to take our arguments, which were pi over 3, and multiply by the value of 3. Now we just have to go through and simplify where we can. And in our simplified form, 2 cubed is 8. 3 times pi over 3 simplifies down to pi. So we get z cubed equals 8 times the quantity of cosine of pi plus I times the sine of pi. And we can actually simplify this further because we know exact values for the cosine of pi and the sine of pi. So this is 8 times the cosine of pi is -1. And the sine of pi is 0. So we have I times 0. So inside the parentheses, we have -1 plus 0, which is just -1. -1 times 8 is -8. So we started with this complex number z. When we raise it to the third power, it simplifies down to -8.